Welcome to the next in the series of webinars from METTLER TOLEDO AutoChem. The topic for today's webinar is Gaining Insights into Difficult Chemistry Using FTIR In Situ Technology. I'm Dr. Jennifer Andrews, and I will be your host for today's presentation. This presentation will consist of a brief introduction to our technology, how it works, and why you would want to use it. Then we will go through 4 hydrogenation case studies utilizing FTIR: a nitrobenzene reduction, a Rosenmund reduction, a Pyrazine reduction, and a reductive amination. We will then discuss the capabilities and advantages of using the FTIR, and will end with your questions and some discussion. The FTIR is a real-time, in-situ mid-infrared system. The technique that we utilize in our sampling technology is attenuated total reflectance, or ATR. ATR works on the principle of Snell's law, where each reflection is actually an interrogation point of the sample matrix. At each interrogation point, the infrared radiation penetrates into the reaction matrix only on the order of approximately 2 micrometers. Therefore, the path length is equal to the depth of penetration times the number of reflections. Since the infrared radiation only penetrates into the matrix such a short distance, color is not a problem, the reaction matrix can be clear or black, and bubbles and solids are not a problem for our probes. In most cases, the system will not be able to observe the solids in the sample matrix. Real-time in-situ reaction monitoring, as we all know, is incredibly difficult for any analytical technique. The reason why we have been so successful and the secret to this success is our COMP probe technology. The COMP probe was introduced in 1994 and has been used by the market for over 12 years now. It is a robust technology that has been used in thousands of applications by hundreds of different companies. The design shown to the right has a zinc selenide focusing support element that focuses the infrared radiation into the ATR sensor, which interrogates the sample. Then the zinc selenide element focuses and directs the infrared radiation back to the instrument. The zinc selenide element does not come in contact with the chemistry, as it is inside the metal housing of the probe. The only wetted materials are the standard alloy C276 metal housing, a thin gold seal, and the ATR sensor. The most universal and widely used ATR material is diamond. However, diamond does absorb in the mid-infrared between 2250 and 1950 reciprocal centimeters. Thus, if you need to monitor in that region for components such as metal carbonyls, isocyanates, or nitriles, then we have the sensor materials of silicon and cubic zirconium available. In addition to the gold seal, we also have a Teflon seal available, and most any type of metal can be used for the probe housing. Specifications for the probe are a standard temperature range of -80 to 200 C, with a special design that will go to 400 C, a standard pressure range of vacuum to 100 psi, a high pressure design to 1500 psi, and a special ultra high pressure design for pressures to 4500 psi. The COMP probe design is available in 3 diameters of 6 mm, 16 mm, and 25 mm. Any of our probes can be used on any of our systems, which will allow you to monitor from very small volumes for discovery through process development and optimization. We also have a classified area system that will allow you to follow your scale-up work at pilot plant and plant levels, as well as monitor hydrogenations or any type of high-pressure chemistry and high-pressure bays. Now that we understand how the technology works, why would you want to use FTIR? Well, when performing reaction analysis, monitoring, and control, challenges that are typically encountered are that reaction kinetics, selectivity, reactivity, and endpoint vary from batch to batch and on scale up. Relying on offline analyses affords being inaccurate, time-consuming, labor-intensive, and an operational hazards, not to mention that conventional offline techniques may not be able to directly detect the component of interest, if be able to detect it at all. In regards to hydrogenations, it is difficult to gain an in-depth process understanding based on offline analysis and hydrogen uptake data. Hydrogen uptake only gives you the total amount of hydrogen used by the system. It does not provide the specific components incorporating the hydrogen. The advantages of REACT-IR are that the variations in reaction kinetics, selectivity, reactivity, and endpoint can be detected in real time without taking samples. It is a real-time, in situ, non-destructive technique providing timely and safe data acquisition continuously. Chemical bond-specific dynamic information provides insight into reaction pathway, mechanism, and key control parameters. Essentially, we are monitoring the making and breaking of chemical bonds, which ultimately gives the chemist or engineer a molecular video of their process. Our first case study is the nitrobenzene reduction. The nitrobenzene reduction is a common reaction for producing intermediates that are used in the synthesis of APIs and fine chemicals. The reduction of nitrobenzene to aniline is a very exothermic reaction, which is also oxygen sensitive. Understanding this reaction is difficult as samples must be pulled with the reactor under pressure. Further, conventional offline techniques are challenged by the instability of the reaction intermediates and products, as well as being labor-intensive, especially when trying to track reaction progression and/or determine kinetics. Also, accurate determination of the reaction endpoint is often not possible by offline techniques. Whether partially reduced hydroxylamine or fully reduced aniline is the desired product, the selectivity and reactivity of the reaction depend on multiple variables: solvent type, catalyst properties and quantities, temperature, hydrogen pressure, mixing quality, etc. Here in the next slide, we can see the key intermediate concentration profiles and kinetics from the REACT-IR. The relative concentration profiles and their corresponding component spectra were generated by our CONCERT algorithm. CONCERT is a proprietary algorithm of METTLER-TOLEDO's which takes a given region of the spectrum and a given time frame of the reaction and deconvolutes this data into the components that are changing at different rates. Having reference spectra, such as the one of phenylhydroxylamine, help to validate the CONCERT results. This reaction with DMSO used in the methanol solvent produces phenylhydroxylamine accumulation but delayed aniline formation. Thus, this reaction scheme is good for phenylhydroxylamine production. Here in the next slide, we have simple peak height profiles from the REACT-IR data of one of the nitrobenzene bands and one of the aniline bands, which show a direct conversion of nitrobenzene to aniline and a great, what we like to call, X-plot. In this reaction, no DMSO was used. We observed no phenylhydroxylamine accumulation and have aniline formation by zero-order kinetics. Thus, this reaction scheme is good for aniline production. In this slide, you can see how well the REACT-IR determines the endpoints of the two reactions. In the reaction with DMSO, here on the left side of the slide, the phenylhydroxylamine endpoint is at 2 hours, whereas the delayed aniline formation endpoint is not until approximately 5.5 hours. In the reaction without DMSO, here on the right side of the slide, the direct conversion of nitrobenzene to aniline takes place in only about 2 hours. Continuing with the same class of chemistry is a nitrobenzyl substitution. The most important issue with this reduction is the immense heat release, which can cause a potential heat transfer difficulty in scale-up. Thus, the development approach is to monitor the reaction kinetics in real time to better understand what causes this heat release. Here we have the heat flow and hydrogen uptake data. You can see the huge heat release during the first part of the hydrogenation. As the hydrogenation progresses, a second slower regime occurs. Although the heat release is large, only the first regime is critical to safety control. The vessel used in scale-up must be able to handle this first initial heat release. However, during the second regime, it is important to know if the product is continuing to be formed or instead if a side reaction is taking place and impurities are forming. With the real-time REACT-IR data, we can see that in the first regime, shown on the left, with the time axis coming out of the screen from 0 to 80 minutes, the nitrobenzyl starting material is quickly consumed and there is delayed product formation. If we look at a slightly different region of the mid-infrared spectrum, shown to the right, with the time axis going into the screen from 20 to 100 minutes, we observe the formation of a key hydroxylamine intermediate, which further hydrogenates to form the aniline product during the second regime. No side products are observed. Again, the overall heat release shown here for this hydrogenation is large, but it is most important to control during the first regime. It is important to have the REACT-IR data to be able to manage the heat release and transfer during the first fast kinetic regime in a large-scale operation. This release transfer is dependent upon many factors such as a change in catalyst, which is common in scale-up, mixing effects, and etc., all of which could cause impurities to form, which could affect the rate of release. The REACT-IR can immediately detect changes such as delayed intermediate formation to the appearance of impurity bands. So in summary, the progression of the nitrobenzene reduction varies widely with conditions. The effect of solvent type or additive to the solvent, the effect of catalyst type, properties, load, treatment procedure, and effects of temperature, pressure, and mixing. Offline analysis may not be reliable due to the oxidation of the hydroxylamine intermediate and possible overreduction due to a delay in the analysis. Therefore, the REACT-IR data is very important as it provides real-time chemical content specific information on the concentration profiles, reaction kinetics, the intermediate identification such as the phenyl hydroxylamine, and the end of reaction. Continuing to our next case study is the Rosenmund reduction. It is one of the most useful methods for the preparation of a large variety of aldehydes from acids. The reduction faces various challenges such as a side reaction which forms an anhydride. This side reaction not only results in direct yield loss due to inertness of the anhydride to hydrogenation, but also imposes batch-to-batch inconsistency due to variations in the amounts of acid and water present in each batch. Moreover, the anhydride may trigger further side reactions that not only introduce additional impurities but also cause further yield loss. Conventional offline techniques are limited, particularly in detecting the anhydride. As has been stated previously, they are labor-intensive when tracking reaction progression and/or determining reaction kinetics. Also, endpoint determination is often not possible by offline techniques. This shown Rosenmund reduction has several process issues. Slow and incomplete conversion, greater than overnight, even with additional catalyst, and a wide variation of yield, 50 to 96%, with the formation of a dimeric impurity. The development approach was to gain a fundamental understanding of the reaction and for the process to obtain high and reproducible selectivity and yield. The incomplete conversion could be due to anhydride formation from water intrusion into the system. Water can react with the acid chloride to form an acid, which can react with the acid chloride to form the anhydride. This anhydride is not detected by the HPLC assay. To perform the HPLC assay, the sample must be derivatized. An amine is used to form the amide for the HPLC. However, this converts both the acid chloride and the anhydride, so it's difficult to differentiate between the two with HPLC. On the next slide, an important note for this reaction is that before the hydrogenation was started, water was intentionally added to the system so that the anhydride would form. In the real-time REACT-IR data, you can see the acid chloride band decrease as soon as water is added and the anhydride form. Looking to the REACT-IR profiles in the bottom right of the slide, once the water is added, the REACT-IR immediately detects the key side reaction with the anhydride formation. Please note, at these hydrogenation conditions seen on the bottom left of the slide, the anhydride will not hydrogenate, which is why it remains stable. Once the hydrogen feed starts, the acid chloride is converted to the aldehyde. With the use of the REACT-IR, the researchers were able to investigate different conditions and mechanisms. They were able to determine that under certain conditions, the anhydride would react with the aldehyde to form the unwanted dimer impurity. At 20 degrees C, the anhydride will not hydrogenate, but at 80 degrees C, it will. They also found that by using the catalyst modifier thioanisole, they could block the dimer formation, for it is very difficult to ensure that no water intrudes into the system. In summary, offline analysis by HPLC failed to detect the anhydride, a key byproduct. The inertness of the anhydride is the cause of the incomplete conversion. The REACT-IR revealed the anhydride formation and in its inertness to reduction. The anhydride formation was the key to the incomplete conversion, the cause of the formation of the dimer impurity, and the key to poor selectivity, low and inconsistent yield. The REACT-IR monitoring of the reaction in real time without sampling helped to gain a fundamental understanding of the process problem and to develop a robust, high-yield process. In the next case study, we are investigating the intermediate step of pyrazine carboxamide to piperazine carboxamide, which is part of the heterogeneous hydrogenation of pyrazine 2,T-butyl carboxamide. This hydrogenation can go through a dihydro and a tetrahydro intermediate. We want to investigate this step to gain a better understanding of the reaction kinetics, the key intermediate, and the critical variables, so we have control and thus a high degree of selectivity, yield, and robustness in scale-up. Looking at the heat flow and hydrogen uptake data, we observe a large heat release at first, then a slower conversion after 15 minutes into the hydrogenation. We need to understand and control this first heat release for safety and investigate the slower regime to see if product is continuing to form or if side reactions are occurring and impurities forming. At 60 degrees C, the real-time REACT-IR data shows the formation of an intermediate which appears to quickly react to form product. The hydrogen uptake data suggests the intermediate is the tetrahydro form since it has taken 2 equivalents of hydrogen. If we look at the REACT-IR profiles here in the next slide, we can see the quick reactant to intermediate conversion with the slight delay in product formation. The question that we must investigate is if the intermediate is stable with temperature. At 35 degrees C, we observe the intermediate form and remain stable. If we again look at the FTIR profiles, here in the next slide, we observe a stable intermediate and a much slower product formation, which sacrifices productivity. Utilizing the in situ FTIR data, the chemists are able to balance temperature and safety to design a safe, productive, and high-yield process. So in summary, the sequential nature of the reaction was understood using the FTIR. We observed two kinetic regimes: the pyrazine to tetrahydro intermediate, which was very fast and impacts the safety of the reaction, and the tetrahydro intermediate to piperazine, which was very slow and impacts the quality of the product and the efficiency of the process. The rates of both kinetic steps are sensitive to temperature. A lower initial temperature reduces the heat release from the first step and improves the safety, and a higher temperature in the second step increases the reduction rate and improves efficiency. The rate and the end of the reaction was observed in real time, saving development time with information-rich data, avoiding unreliable determination of end of reaction, and isolating an intermediate as needed. The last case study we're going to discuss is a reductive amination. Reductive aminations are a frequently used synthetic methodology to form carbon-nitrogen bonds. They involve the formation of a reactive imine intermediate and subsequent reduction by heterogeneous hydrogenation. A heterogeneous hydrogenation is favored over the metal hydride approach due to the costly reducing agent and multiple steps involved in the metal hydride synthesis. Imine intermediates are often unstable ex situ. They're prone to degradation by hydrolysis and are therefore challenging to monitor with conventional offline analytical techniques. Besides, multiple grab sampling of a reactor under hydrogen pressure is time-consuming and may significantly increase batch cycle time. Finally, difficulties can be encountered with batch-to-batch or reactor-to-reactor variability introduced by mass transfer effects, starting materials, and catalyst quality. Accurate detection of the hydrogenation endpoint is important in order to avoid overhydrogenation and the formation of impurities such as a dimer. FTIR monitoring is preferred to the conventional hydrogen uptake monitoring since it provides component-specific information and is more sensitive to detect the onset of product degradation upon overhydrogenation. From the FTIR data, once the amine is formed, it almost immediately will begin to degrade to form the dimer. So the challenges are the amine stability, which can introduce impurity and yield loss. Over-reduction results in impurity and dimer impurity and yield loss. A lack of development time. The customer needed to go from 1 liter to 100 liters directly to support clinical trials. Only one pilot plant batch was required, so there was no room for failure. The solutions provided by the FTIR technology were that the amine formation and consumption can be monitored real-time in situ. The end of reaction points can be observed timely without taking samples, and the real-time monitoring and control from 1 liter to 100 liters. With having no prior experience of the process behavior at the 100-liter scale, the ability to get dynamic information on reaction process is crucial importance to ensure the level of control required to avoid batch failure. The data shown here is from the 100-liter pilot plant run. On the bottom right-hand side of the slide, you can see the DICOMP probe integrated into the end of a dip tube inside the glass-lined reactor. In the upper right-hand corner of the slide, notice how isolated the amine peak is. Thus, it was used directly from the lab scale 1 liter run. It required no calibration for the scale-up run. The FTIR peak height profile of the amine band shows the quick formation of the amine and its stability during the post-stir period under the reaction conditions defined during process development. Once the hydrogenation begins, the amine reduces to form the amine product. At the 1 liter scale, the hydrogenation took approximately 10 hours, and at the 100 liter scale, it takes only approximately 2 hours. The hydrogen feed was stopped as soon as the amine peak profile plateaued to avoid overhydrogenation. Again, there was no room for failure for this single batch. We believe the time difference for the hydrogenation on scale-up is due to both mass transfer and mixing effects and was expected by the project chemist and engineers. So in summary, the amine formation and consumption was monitored in situ real time. The end of the amine formation was observed clearly, and no detectable amine conversion during batch holding. The rate and the end of the hydrogenation was observed in real time. The hydrogenation follows zero-order kinetics. The hydrogenation took 5 times longer in the 1 liter than the 100 liter. The hydrogenation rate may be limited by gas-liquid, mass transfer, and mixing effects. And the FTIR ensured a successful clinical trial batch to follow the right first-time delivery of product. Hopefully these 4 case studies have shown the capabilities and advantages of the FTIR, which in review are continuous monitoring of reaction components, the reactant, intermediate, product, byproduct, and purity, reaction progression, initiation, dynamics and rate, endpoints, concentration, gain a fundamental understanding of reaction kinetics, pathway and mechanism for fundamental understanding of the critical process parameters, the boundary conditions for safety and control, for process efficiency and robustness, yield, productivity, reproducibility, and for consistent product quality, purity, specifications, variability. The FTIR performs in situ real-time analysis of components difficult to analyze otherwise, of oxygen or water-sensitive mixtures or unstable reaction mixtures, of highly toxic, hazardous, or explosive reaction matrices, at extremes of temperature and or pressures, and all without perturbation, intrusion, or material loss. The FTIR affords successful and fast development and scale-up. You can monitor and control in real time from bench scale to production scale, gain chemical-specific and information-rich data from limited batches when you have limited time for development, limited material for experimentation, and limited other resources. And finally, the FTIR allows for continuous learning and improvement, can record, observe, and analyze detailed changes from batch to batch, catch differences throughout reactions between batches, and obtain critical information difficult to have otherwise. Can gain insight into the root causes of process problems, change or optimize existing processes for better performance, and design better processes for the future. We would like to thank the following contributors of Merck & Company, where several of these studies were performed, and our colleagues Dr. Jian Wang and Dr. Claude Didigeron for their contributions to these studies. Thank you for your time today.